Hello, in this video, I will introduce our work, TEESlice, slicing DNA models for secure and efficient deployment. I am Ziqi Zhang from Peking University. Machine learning models are regarded as software 2.0 and is a new software generation. MLAS is a common practice for technology companies to provide ML services. The companies employ developers, collect datasets, use high-performance servers to train AI models. Once the models are trained, they can be used to provide ML services, and the companies can charge the users for the service usage. Three different aspects should be considered when companies providing ML services: security of AI models, privacy of users' data, and inference latency. The AI models are important intellectual properties of the company. A stolen model may lead to a loss of thousands of dollars. Besides, it may make it easier for the attackers to craft adversarial examples. For the user's privacy, nowadays, governments have strict regulations on the protection of user data. Companies may be fined by a large sum of money if such privacy is breached. Inference latency affects users' experience, especially for the applications of mobile scenarios. Existing MLAS solutions can be divided into three categories. The first type is based on cloud servers. The users upload the input data to the cloud server, and the server returns the model prediction. The problem of this type of solution is the risk of privacy breach and high latency. An attacker may pick the user's data during the internet communication process. The upload and download procedure cannot satisfy the real-time requirements of mobile applications. The second solution is based on cryptographic technologies, such as homomorphic encryption and multi-party computation. The users and the model owner encrypt their own data on each side and collaboratively compute the model output. During this process, neither side can interpret the data information of the other side. The shortcoming of cryptography is the high latency. Both sides have to communicate at every DNA layer, and the computation on the encrypted data is slow. The last solution is that the model owner sends the model to the client users and perform inference on the user's device. However, sending the model to the users violates the security of AI models. But we can resort to the trusted execution environments on the user's device. The model owner can send the model to the TEE and perform computation inside the TEEs. In this way, the AI model is guaranteed to be secure. Trusted execution environment is a secure area on the main processor to provide data and code confidentiality. The computation process and data are all encrypted. TEEs can guarantee the computation isolation, data sealing, and remote attestation. Isolation means the code and data inside the enclave's protected memory cannot be read or modified by any internal process. The data sealing means the data in the untrusted host is encrypted and authorized by a hardware resident key. Attestation provides an unforgeable report attesting to the code and data. But the high security of TEEs come with performance degradation. Tees usually have limited internal memory. The memory of Intel SGX is around 93 MB, and the memory of TrustZone is around 10 MB. Using exceeded memory introduces additional overhead, which mainly comes from the CPU mode switch and data encryption and decryption. As shown in the figure, once the required memory exceeds 90 MB, the computation time increases by a large margin. Thus, putting the whole DNA model inside Tees is viable, but inefficient. The computation process of DNA model usually requires enormous memory. As shown in the table, the DNA memory usage is much larger than the T limitation. So how can we optimize the model performance inside the T's? Our solution is to slice in DNA models and split a DNA model into two parts. The privacy-related slice contains the private information of the model owner and is secured by the T. The privacy-excluded backbone has no sensitive information and can be put on the untrusted AI accelerators. We focus on a two-party scenario, including a model provider P and a model user U. P provides the functionality of the DNA model and charges for the usage. The defender's goal is fourfold. Data privacy and model privacy should be protected against the other party. T integrity means the probability that the framework produces an incorrect output is less than T. Finally, the inference process should be much more efficient than the vanilla T-based implementation. The proposed framework, TEESlice, consists of two stages: private slice extraction and hybrid model deployment. In the first stage, given the private target model, the defender downloads a public model and trains the private slices from the target model in a semi-supervised manner. A generative network is trained simultaneously to enrich the training data. The output of this stage is a hybrid model that consists of public model backbone and private slices. In the second stage, the private slices are deployed inside Tees, and the public backbone is put on the untrusted AI accelerators. The memory usage of Tees is optimized, and all the data computation between the two environments is encrypted. The goal of semi-supervised learning is to supply diverse training data, as the defender may not have all the data during the time of slice extraction. Thus, we train a data generator along with the student model iteratively. The generator consistently generates synthetic data to improve the student model. The hybrid model is derived from a densely sliced model. The defender attaches dense slices to the public model and trains the slices. The training objective is to force the hybrid model to mimic the behavior of the target model. The slices are then pruned in a static manner, followed by an iterative manner. After pruning, only a small amount of slices remained, and the workload inside the T is optimized. In the next stage, we have to solve three challenges: how to deal with the T's limited memory, and how to eliminate the leaked information of input-output features. The third is how to verify the correctness of the outsourced DNA layers. To solve the first challenge, we implement a memory manager that actively switches memory chunks into and out of the T's. Thus, the overhead of CPU mode change is reduced. For the second challenge, all the feature communications is encrypted. The feature map is encrypted by one-time pad inside the TEES. The computation in the untrusted environment is performed over the encrypted data, and the output feature is decrypted in the tier. The correctness of computation is verified by the free-vault algorithm. We implement TEESlice with Intel SGX using PyTorch and official SGX SDK. We evaluated TEESlice on CIFAR10 dataset with RedNet 18, RedNet 50, and RedNet 101. Experimental results show that the inference throughput can be improved up to 14 times. To conclusion, we propose to slice a DNA model into two parts so that a commercial model can be efficiently and securely deployed on the user's device. We design a framework, TEESlice, that can first extract private slices in a semi-supervised manner. Second, minimize the computation workload inside TEES. Third, safely deploy sliced private model across TEES and untrusted AI accelerators. We implement a prototype with Intel SGX and evaluate the performance. Experimental results show that TEESlice achieves up to 14 times speed up in terms of the inference throughput. Thank you.